In this webinar, we'll be discussing parallel and distributed optimization with Gurobi Optimizer. Now, I'd like to introduce you to the Director of Engineering and Support at Gurobi Optimizer, Dr. Greg Glockner. Greg has trained users of optimization software around the world. He is an expert in optimization modeling and software development. With that, thank you again for joining us today.
Thanks, Jessica. So again, our subject for today is parallel and distributed optimization. Before we get into these topics, let's talk about some terminology. So parallel computation, for today's talk, when I use that phrase, I'm meaning about one computer with multiple processor cores and one or more processor sockets, meaning one or more chips, each with multiple processor cores. Now, parallel computation has been part of Gurobi throughout our history, and we have it in several different ways. We have mixed integer programming branch and cut does parallel computation. So does the barrier algorithm for continuous optimization, that is linear programming, quadratic programming, and second-order cone programming. And finally, concurrent optimization, which I'll talk about in a little bit. Distributed optimization is a slightly different concept. With distributed optimization, you use multiple computers linked together via a network. This is a relatively new feature for Gurobi Optimizer. And the interesting thing is that distributed computation uses parallel computation because each independent computer can do parallel computation. In fact, not only can it, it does. So it does parallel computation within distributed optimization. We'll talk more about that a little bit later. So what are parallel algorithms and how do they link up with hardware? When you've got parallel algorithms, you have to design them around the hardware, that is around the physical computer that you're using. You have to decide what work should be done in parallel, and that makes a decision on how much communication is required. You have to factor how long that communication will take. Your goal with parallel computation is to make the best use of your available processor cores. You don't want cores to be idle more than necessary. So let's take a look at some pictures that represent the computer hardware. So your standard multiple core computer has a processor with one or more computing cores. All computers nowadays have this structure, from even the most basic laptops to the desktop and servers that you might find. These cores and this processor has memory that's used to store all of the computation, and in that memory there's a bus, and this bus is the bottleneck between the processors and storing and retrieving data from the memory. This gets a little bit more complicated with distributed computing because not only do you have the bottleneck on the memory, but you've got a huge bottleneck on the computer network that links one computer with the other computers on the distributed computing network. So what is this bottleneck like? So a bottleneck between the computing cores and the memory that's inside of that computer, it's fast, it's not instantaneous, but it's pretty fast. But when you start to look at the network, it's much slower. It's about 1,000 times slower than the memory bottleneck inside of a single computer. Now, there are some things you could do to reduce that network bottleneck. You could go to a supercomputer where they can have very, very fast communication from one computer to the next. But even on a supercomputer, the communication from one computer to the next is still much slower than the communication inside of a single computer. So when you're designing the algorithms, you really have to think about how that network connection is going to affect the algorithms. So let's talk about the distributed algorithms that you could find in Gurobi Optimizer 6.0. In 6.0, there are 3 distributed algorithms. There's distributed tuning, distributed concurrent optimization. MIP was actually available before 6.0, and in version 6.0 we added linear programming distributed concurrent optimization, and then distributed MIP, which I think is the most powerful of these, and we'll understand why in a few minutes. So first let's start with distributed tuning. So when we talk about tuning, we look at MIP models where there are lots of parameters. For example, you could bias the MIP towards finding feasible solutions. You can also bias or focus the MIP towards improving the bound. And so tuning performs a set of test runs to find better settings for a particular model. The default settings are designed to be fast across a wide variety of models, but for any particular model, for your particular model, there may be parameters that will be faster than the default settings. Now, these models are these parameter tests are completely independent, and so this is a very obvious candidate for solving in parallel, and in fact, in solving on multiple computers with distributed optimization. So distributed tuning is a clear win for this model development activity. If you've got 10 machines, doing distributed tuning on those 10 machines is approximately 10 times faster. So this is just an obvious thing to test. If you've got 10 machines and you need to do some parameter tuning during your model development, use distributed tuning to do that. It's a very, very useful feature. But this is something you just do during model development. Let's talk about the algorithms that can be done for parallel and distributed when you're actually solving a model. So let's start with talking about concurrent optimization. So in general, concurrent optimization is when you run different algorithms or different strategies on different machines or different cores. And the first one that finishes is the winner. That's the one that returns back a solution. So concurrent optimization is something you could do both in parallel on one computer or in distributed on multiple computers. Because these are independent solves, it's an ideal case for distributed optimization. The communication is relatively small. You send the model to each machine, and each machine solves independently. When the first set of parameters finds a solution, it returns the solution back, and that's the winner. So for concurrent linear programming, the default behavior is to use different algorithms. You can use primal simplex, you can use dual simplex, and you can use barrier. For MIP, you've got the opportunity to use lots of different strategies. For example, you can use MIP Focus 1 or MIP Focus 2 to focus on finding feasible solutions or focus on optimality. And if you don't change the behavior of the concurrent optimization for MIP, then the default strategy is to try different seeds rather than different algorithms. And it's actually very easy to customize via concurrent environments, and I'll have an example of that in a few minutes. So let's look at some results for solving distributed concurrent MIP. This MIPLIB 2010 test set is a set of over 300 mixed integer programming models that were collected by Gurobi, but were collected by an academic and industrial community. This is used in lots of popular benchmarks for mixed integer programming. And so we'll take a subset of that, 87 of the 361 models. The reason that we're going to use that subset is these are models that were solvable 5 years ago. We're not going to look at the models that were impossible to solve, that couldn't solve within a reasonable time limit. We're actually going to look at the models that were solvable 5 years ago, but in fact, nowadays, because Gurobi has improved in his performance, it can solve a much larger number of these models in the same default time limit. But for the reports I'm going to show in a moment, we'll look at 87 of the MIPLIB 2010 test set. Now, this isn't designed as a high-performance computing test set because, in fact, many of these models are simple. Many can solve, over 2/3 can solve in less than 100 seconds, less than 2 minutes. In fact, 8 models solve at the root node, and about 1/3 solve in fewer than 1,000 nodes. So this is not necessarily the hardest set of models. This is just supposed to be a representative sample of real-world models. So let's look at distributed concurrent MIP for this test set. And so let's compare the results of 4 machines versus 1 machine. On all the models, that is the models that take more than 1 second, not the trivial models, distributed concurrent MIP is faster in 38 of the cases and slower in 20. And so it gets an average speed up of about 1.26 times. On the harder models, that is the models that take 100 seconds or greater, distributed concurrent MIP is faster in 17 cases, but it is slower in 3 cases. Now that's on 4 machines. With 16 machines, the speed up is a little greater, both in the smaller models and across the board with the larger models. So one of the questions you might have is, well, why is it worse in some cases? And typically it's worse because there's some communication time. And if you're waiting for that communication in the setup of concurrent MIP, That's time you could have been solving it if you were just solving it directly on one computer. So there are some cases that it is slower. So there's not always a win, just like every other strategy in mixed integer programming. But on average, distributed concurrent MIP can help solve models faster. Now, as I said a few moments ago, you've got a default behavior, but you can't customize it yourself. For example, what if I wanted to solve it with two strategies, one with aggressive cuts and the other with aggressive heuristics? Now, I wouldn't necessarily want to solve these at the same time because the aggressive cuts might be slowing down the time I could be spending generating heuristics. On the other hand, when I'm generating heuristics, I might not be improving the bound. So if I could use two computers together, I could use those two computers to each with these different strategies. So this is an example where I don't want to use the default strategy, and I could do that very simply by creating two concurrent environments. So here's an example in Java, and this is just a fragment of my code, but in my code, I take my model object, that would be the GRB model object, and I call the get concurrent environment twice to get two different environments. I'm going to call these env0 and env1. And then on env0, I'm going to set the cuts parameter to 2. And on env1, I'm going to set the heuristics parameter to 0.2. I'm then going to optimize. And when I'm done optimizing, I retrieve the solution, but I also can clean things up by discarding the concurrent environments. The nice thing about this code is that it will work the same if I want to do concurrent optimization on a single computer or if I want to do concurrent optimization on two computers. This is an example in Java, but you could do the same code in C++, in Microsoft.NET, in Python, and in C. Basically in all of the object-oriented interfaces and in the C interface. I just use Java because it's a very popular language and it's easy to see the syntax here. So that's all about distributed concurrent. Let's talk about distributed MIP. So this is a bit more complicated. The distributed MIP uses an architecture that has a manager and worker paradigm. The manager is going to send the model to all of the workers, and it's going to track the solution information, specifically the dual bound and the worker node counts. At various times, it's going to rebalance the search tree to put a useful load on all workers. In other words, it's trying to keep workers from being idle too much. And when it finds a solution, it needs to let the workers know that a better solution has been found. The worker's job is to solve MIP nodes and report its status, and when it finds new feasible solutions, report it back to the manager. And this is synchronized deterministically. This is very important because it does change the performance if you start to use computers that are not identical in performance. But that's also good because, again, you'll get the same results each time you run it. You're not dependent on timing-specific information. So there's two parts to distributed MIP. There's what we call the ramp-up phase and then the main phase. So the ramp-up phase is an initialization part, and in fact what distributed MIP does is it uses the distributed concurrent that we talked about a few minutes ago to initialize distributed MIP. So it takes the same problem and solves it identically on each worker, but each worker using different parameter settings. So each worker starts by solving the problem from scratch, but with different parameters. And after a certain amount of time and it's explored enough nodes, then the ramp-up phase stops. Now, in some cases, of course, the concurrent MIP will solve the problem, in which case we're done. But if we reach that other stopping criterion, then that winner is reported back. That's the worker that made the most progress. And so when that happens, then we enter the main phase. And so we discard all of the worker trees except the winners, the one that made the most progress. We collect the nodes from the winner and now start to distribute that remaining tree among the remaining workers. And then each worker starts solving the tree on its little part of the tree. And then periodically this gets synchronized to rebalance the load. And that balancing of the load, balancing of the search tree is key because distributed MIP doesn't help in every single case. So there are some cases that distributed MIP is no help at all. You know, if you've got an easy problem, why bother with all this extra overhead? If this model solves in a fraction of a second, distributed MIP is unlikely to help and in fact is likely to make the problem solve slower. Also, if you've got a very small search tree, you're not going to see much from parallelism. Lots and lots of models that we see solve at the root node. And those are great models, and many of them are very important MIP models, but unfortunately those are models that won't benefit from parallelism in the MIP. They might benefit from parallelism in the LP relaxation of the MIP, and that's just like distributed LP or concurrent LP or parallel barrier LP. But if the search tree is small, then the distributed MIP is not going to give you much benefit. Also, and this is this picture at the bottom, I hope you could see it, is an example of an unbalanced search tree. You could sell this tree with distributed MIP, but what's going to happen is that part of the tree is going to go to one worker that's going to do a lot of work, and the a remaining part of the tree will go to workers that'll solve one node and find out it's pruned or it's infeasible, and it'll then be stuck waiting for the other nodes to synchronize. And so that worker will be idle, and you don't get much of a benefit from distributed MIP in that case. So what do the cases look like when you get a lot of benefit from distributed MIP? They have two properties. One, the search tree is relatively large, and the search tree is also well balanced. So there's many nodes in the frontier that lead to large subtrees. And you can see that in this picture. You can see that if you break up the tree, you've got lots of large subtrees, and each of those subtrees can be solved very nicely and very effectively by a separate computer. So let's talk about performance, because I think that's the thing that we get most excited about. And so when I talk about that, I'm going to show you some benchmarks so we can compare what's the performance of traditional parallel MIP and what's the performance of concurrent and what's the performance of distributed MIP. And to do that, let's take 3 different views of 16 cores. So we're going to take 3 different tests, all using a single computer with 16 cores. We could use that 16-core machine as a standard parallel optimization. This would be the way you would have always done it with Gurobi Optimizer. We could also use this 16-core machine to run the distributed code on 4 core subsets. And then, of course, we could look at it as separate machines, 4 four-way machines to run the distributed code. So in other words, in the first 2 cases, we're in a single machine. We don't have that network communication to worry about. And on that 4 machines, now we've got the network communication and run the distributed code. And so our question is, which is going to give the best results? So before we get to that, let's just take a quick picture of what this looks like. If we have one 16-core machine, this could have 2 processor chips, each with 8 cores, and it has some shared memory. And we could subdivide this computer to treat it like 4 independent computers, so we could treat them as 4 4-core machines. And we could also look at it as 4 independent computers linked together in the network. This is just the thing I said earlier, given to you in a picture. So let's look at this one 16-core machine and see what the performance is like running it in a couple of different configurations. So first, most models, that is the models that solve in 1 second or greater in this first column, treating that model as one 16-core machine, you get a 1.57x speed up as you compare it with a 4-core, meaning what would it be to go from 4 cores to 16 cores? You get 1.57 times faster. Interestingly enough, to treat it as 4 4-core computers, you still get a speed up, but that speed up is less than treating it as one large computer. If you look at just the larger, harder models, that is the models that take 100 seconds or more, then you get about a 2.00x speed up on treating the computer as one large 16-core computer. You still get a pretty large speed up, though not quite as large if you treat it as 4 independent computers. So the message of this slide is to say, if you've got one large computer, you're better off not using these distributed algorithms. You're much better off using traditional parallel MIP, letting the optimizer itself treat it as one large computer and distribute the MIP search tree using that one computer as one large machine. But the nice thing is, yeah, it's slower to treat it as 4 separate computers, but it's not that much slower, especially for the large model. So this gives us some hope when we're going to start to use not one large computer, but use a series of smaller computers. So now let's look at that second case. Let's say, what if we wanted to treat it, instead of using one large computer, let's compare it with 4 smaller computers. So here's that same computer treated as one large computer, and now look at 4 smaller computers. Now for all the models in the test set that solve greater than 1 second, the large computer outperforms it, 1.5x faster versus 1.43 times faster. For the larger models, though, this is where things get interesting. In fact, the 4 independent machines are slightly faster. Now, you might wonder, well, why? You've got that one fast computer, and when I said earlier, that there's faster communication, but in fact, there's other things going on inside of a large computer where there are some resource limitations, in particular the memory, when all the processor cores are trying to access the memory nearly simultaneously. So in fact, for independent computers can be a very effective way to solve models. So of course, now this becomes the question is, are you better off with one large computer or 4 independent computers? And there's a set of trade-offs in that. 4 independent computers actually tends to be cheaper than one large computer. You can go out and buy computers nowadays for about $1,000 plus memory that are very, very powerful. And so 4 of them is $4,000 or $5,000 US. But one large computer is quite a bit more expensive than that. But there are some trade-offs. 4 independent computers means more parts that could fail and need to be replaced. It's also more administrative work. You have to get them all, you get the computers plugged in, installed, configured, get them their different system updates. Each time we release a new version of Gurobi, you now have to install it on 4 independent computers. So there's more administrative work when you have 4 independent computers. So there's no single situation that fits everybody's situation, but this is a very good sign that you can treat 4 computers together and get some very, very fast run times. So let's look at the change in performance as we go from 2 to 4 to 8 to 16 computers. Again, looking at this MIPLIB 2010 benchmark set on a Intel Xeon processor and compare it against the standard code on one machine. So 1.0 means the solve time on one machine. So with 2 machines, you get faster performance in 40 out of the 56 cases, and you get a speed of about 1.14 across the full set of models, that is the models that solve in 1 second or greater. For the harder models, you get a greater speed up, 1.27x. As we go from 2 computers to 4, you get a big improvement in speed. You get more models that are solving faster, both of the full set and of the larger models. But it's not linear. As you go from 4 to 8 computers, it doesn't get twice as fast. It gets faster. The full set gets a bit faster. It goes to 1.53, or about 0.10 times faster. The full set of larger models gets faster, but again, it's not twice as fast. And going to 16, you get additional speed up, but not much for the full set of models, though you still get a nice speed up for the harder models. So there is a point of diminishing returns. We don't often test it ourselves with more than 16 independent machines, just for this very reason, is that there is a point of diminishing returns that you don't see so much benefit from adding more machines. It seems that that sweet spot is about 4 or maybe 4 to 8 machines. There are some big wins. Here's an example of a model that you could find in the MIPLIB model library. And somebody just a few days ago asked this question on the Gurobi discussion group, said, well, are there any models that get a big win? And in fact, here's one where solving the model with just one machine takes over 2 hours to solve it. But if we go from 1 machine to 16 machines, we get over a 9 times speed up. We get it under 30 minutes. And if we go to 32 machines, this is fantastic. This is about 10 minutes to solve the model. Of course, we need a lot of machines to do that, but this takes a model that took several hours, and to get it down to just over 10 minutes, this is a very, very nice speed up just from going from 1 machine to 32 machines. Now, of course, a few minutes ago I said, well, we have this distributed concurrent algorithm, and we also have this distributed MIP. So which one is better? And so we could look at this. We could solve the distributed concurrent algorithm on a set of models. In the upper table, we've got the full set of models that take 1 second or greater. And on concurrent, we get a 1.26 times speed up. That means it's 1.26 times faster on 4 machines than a single machine. And with 16 machines, it's 1.4 times faster. With distributed, it's quite a bit faster than concurrent. Distributed is 1.43 times faster on 4 machines and 1.58 on 16 machines. And on the harder machines, the lower half of this slide, these are the models that are 100 seconds or greater. Distributed concurrent is 1.5x faster on 4, or 0 times faster on 16 machines, but distributed concurrent MIP is 2.09 times faster or 3.15 times faster. Now there's an interesting thing to see here. If you look at 4 distributed machines is faster than 16 concurrent machines. This really, I think, is a way to see that distributed MIP is a much more powerful method than distributed concurrent MIP. Same thing on the harder models. Distributed MIP on 4 machines is faster than distributed concurrent MIP on 16 machines. So just switching from the distributed concurrent algorithm to distributed MIP algorithm gets you a faster solve times, and in fact faster on a smaller number of machines than you get with just the standard distributed concurrent. Well, of course, that makes you wonder, why do we have distributed concurrent? And the reason is, well, one, it gives you the ability to do the customization, but in fact, it's a subroutine, as I said earlier, to the distributed MIP. It's what's solved in the initialization ramp-up phase of the distributed MIP. So what I hope we've covered here is that distributed MIP gives you the opportunity for some huge performance in some cases. Now, on average, the performance improvements are significant, but they're not always huge. So this is this case where some models benefit greatly, some models do not benefit at all, some models benefit but only modestly. Distributed MIP is much faster than distributed concurrent, so generally you shouldn't use distributed concurrent yourself, but just let it happen automatically in the ramp-up phase for distributed MIP. This is actually as effective as adding more cores to one box, to one computer. So this distributed MIP is a very, very powerful way to solve models. But it's still a challenge for us. This is still something we're going to be studying in our future development at Gurobi, because parallelism is very complicated and difficult. It's something we will continue to focus on. So last but not least, let me talk about some of the mechanics. How do you actually use this in your day-to-day optimization? So first, the way you get it configured on your computer is something that we call Gurobi Remote Services. You install and start Gurobi Remote Services on each of the worker machines. That is to say, if you've got 4 computers, you do need to install Gurobi Optimizer on each of those machines. But the nice thing is we don't require a license key on the worker machines. You just have to install the software. You don't have to purchase or install a license key on those machines. And when you start that Gurobi Remote Services, it's a program that runs in the background and listens for requests for those distributed worker computers. There's a few parameters that you set on the computer that's going to serve as the manager. You tell it that you have concurrent jobs, and you set that to the number of machines you've got, and then you set the worker pool equal to the host names or the IP addresses of the machines that you want to run on. And the nice thing is that you just have to set a couple of parameters. You don't have to make any changes to your code. So any code that you've written today for Gurobi can already start to use distributed MIP. Now there is an additional license for the manager machine. It needs the distributed add-on, and today we limit that to 100 workers. As I said earlier, it's not common to find a benefit beyond, say, 8 workers, and so we've just put although there are a few cases that benefit a little bit beyond 8, we haven't seen any that benefit beyond 100, so we put a limit of 100 workers on there. Remember, there's other overheads such as communication, so you can't just keep adding computers indefinitely and get benefits. So the Gurobi distributed concurrent MIP algorithms and the distributed concurrent algorithms are an integral part of the product. They're built on top of another feature that we call Gurobi Compute Server. And in fact, there's only about 1,500 lines of C code that are specific to the concurrent and distributed MIP. And the nice part about that is because it's built into the C library, the distributed algorithms are available to all of the Gurobi interfaces, including MATLAB, including the modeling systems, and of course including the object-oriented programming languages such as Java, C++, and .NET. So there's no special binaries, there's no different version of Gurobi, it's already available in the programs that you've written today. So any changes that we make in the MIP solver automatically apply to the distributed code too, because each of these computers that are running distributed algorithms themselves are solving parallel mixed integer programming. So any performance gains we get in a future version that will make the standard MIP faster will also make the distributed MIP faster. And of course, we're also going to make improvements to the distributed MIP as well. So I've got a bit of a footnote here. And I want to talk about GPGPU computing. And this is a question that comes up periodically, both on the discussion group and from individual customers. And people ask about this. Now, GPGPU means general purpose computing on graphics processing units. These graphics processing units are these special processors that are in all modern computers. Sometimes they're separate cards, sometimes they're integrated with the motherboard, and they help with the graphics processing, make it go faster. These originally came in from computer gaming, where people want to do lots of 3D gaming, though it's used in other types of graphics as well. These special processors are massively parallel, but they're designed for simple computation. And there's a lot of marketing from the various hardware vendors that tell you that this is a way to get your parallel computation faster, including not just graphics processing, but general kinds of processing. And because of all the marketing that's around this gets people asking us, does these GPUs give you faster computation for things like linear and integer programming? Unfortunately, however, GPUs are not well suited for solvers like Gurobi, and that's for the following reasons. For linear programming depends on sparse linear algebra. Sparse linear algebra, because of its sparsity, that's the sparse matrices that you use in linear programming, that doesn't parallelize well to hundreds of GPUs, hundreds of these graphics processing units. For mixed integer programming, while the MIP tree parallelizes nicely, each tree is doing very different calculations. But the GPUs are based on the idea that each GPU is doing very similar calculations with different data. So MIP, while it does parallelize well, it doesn't parallelize to the architecture that you find on graphics processing units. But we're continuing to monitor this. If that changes, certainly we'll reinvestigate it. But for today, this is not something that benefits the types of computation done by a solver like Gurobi. So, but at the same time, while GPUs have a lot of processing cores, in fact, the general purpose processors also continue to add parallel cores. And in fact, while the general purpose processors add parallel cores, this will benefit Gurobi Optimizer. So last but not least, how do you get to use this? You do need this change in licensing. So for commercial customers, the distributed optimization licenses are not included by default. You must purchase the distributed option, and it's very easy to get. All you have to do is ask your sales representative. But the nice thing is, if you contact your sales representative, we at Gurobi will be happy to perform a benchmark for you, take your sample models and run it on our hardware that we've got to say whether or not you could get a benefit from getting distributed optimization, and if so, what kind of a speed up can you get? And of course, you can also ask your sales representative for pricing information. For academic users, we're happy to provide it at no cost, but it has to be provided on demand for the following reason. We're not including it with the named user licenses, and the site license, unfortunately, that's not currently supported. It's not possible today, given the current system, to include the distributed optimization feature with the academic site licenses. But if you're interested as academic users, please ask your network administrator to contact us, and we'll be happy to provide you a license. But note that that license will be a single machine license. That will be your manager machine, and then that will allow you to do distributed optimization on various computers at your university. Of course, all licenses include parallel optimization. So what I said earlier about distributed optimization being an additional add-on, there's no add-on required for the traditional parallel optimization. So all licenses, including free academic licenses and all commercial licenses, include parallel optimization for a single computer. So what I said about getting an additional license or an upgrade to a license for commercial users, that's for those that want the distributed capability.